All right, so we're going to talk about sketching the locus. So we've been saying, well, we're going to get faster at this. So now's the time. So what we want to do, again, the goal here is to see how the closed loop poles, again, as the gain K changes versus time, how the closed loop poles change. And so what eventually we're going to do is we're going to choose a value of K that's going to hopefully meet our transient, our design goals. And then we'll also look at the next step then will be, if you can't just change K, what else do you need to change? But we'll get to that in a little bit. But right now we just need to understand, as the gain K changes, where do the closed loop poles move to? All right. So sketching the root locus. So we've gone through all this kind of math and all those type of things. Now we just want to get down to, how can I quickly sketch this? So the first thing is the number of branches equals number of closed loop poles. Each branch, so we're going to, some of the lessons that we've learned here, right, we're going to come back to them, but basically each branch begins at an open loop pole and that is when K is equal to 0, and ends at an open loop 0, and that's when K approaches infinity. Okay? The other thing that we need to remember is that the root locus is symmetrical about the real axis. Okay, so why is that? Well, the reason why is that closed loop poles are either real or complex conjugate pairs. Complex conjugate pairs. I mean, I'm sure in a math class they could come up with exceptions to this, but from an engineering perspective, otherwise physically unrealizable. Okay, so that means everything is the same on the top and the bottom, right? So the top, so if you've got a pole above the real axis, then you've got a pole below the real axis. Things are not symmetric about the imaginary axis, right? But what the top and the bottom are going to be mirrors of each other. So let's look at an example here. This is a vertical takeoff and landing aircraft. And there's a lot of control systems on a vertical takeoff and landing aircraft, but we're just going to look at is the elevation here as we're taking off. All right, so our control system looks like this. I've got R of S, That's my desired height. Got plus. I've got a controller here, k s plus 4 over s plus 10. This is a lead controller, but we'll talk about that later. It doesn't really matter at this point. And then we have the plant dynamics, which are s times s minus 1. So notice that the open loop system is unstable. C of s. And then we've got unity feedback. All right, so a couple things in. So remember, we're going to look at the open loop. So for our purposes, right, we can view this block here as k g of s, and h of s is 1, right? There's nothing in the feedback path. So our open loop transfer function is k g of s h of s is equal to k times s plus 4 times s times s minus 1 times s plus 10. Okay, so let's go ahead and sketch this. So we have 1, 2, 3, -5, 6, 7, minus 10, and 2, 3, 4, 5. All right, and then this is obviously the imaginary axis here. So imaginary, real. Okay, so let's go ahead and add the open loop poles and 1, 2, 3, 4, 5, 6. Okay, that's all right. Okay, so let's add the open loop poles, right? We have one at the origin. We have one at +1. So again, we notice that the system is unstable. And we have one at -10. All right, so we have 3 poles. All right, those are the, again, using x's for open loop transfer function poles. And we're going to use zeros for open loop transfer function zeros. Right, and we have one at -4. Okay. All right, and we know where we're going to start, right? We're going to start when k is equal to 0, we're going to be here, right? So k equals 0, we're here, and here, and here, right? So we've got three branches and 3 poles. Now we'll have to figure out, we know one of the poles is going to go to the 0 at -4. I'm not quite sure where the others are going to go, but we'll figure out where to go next. Now, what I would normally do, and I think this is probably a good idea, right, is to have you figure out where the locus exists on the real axis, right? And we could, one way we could do that, right, is use the way to do that, right, would be to use the angle criterion, right? So real axis segments. And we know that the sum of k g of s h of s is equal to the sum of the 0 angles minus the sum of the pole angles. And that has to be equal to plus or minus 2q plus 1 has to be some form of 180 degrees. So why don't you see if you can figure out where along the real axis where we have to be. So if you want to pause the video, that would be great. And we'll go from there. Okay, so, all right, so let's, so we come back here, right? So for example, let's look over here to the right of all. So we have three pole angles. They're all 0, and one 0 angle, which is all 0, right? Because the angle from any of these poles to any location out here and here is going to be 0. So if you add the 0 angles, I've got zeros, add the pole angles, subtract the pole angles, I got 0, so it's clearly not equal to 180. However, if you move in between here, right, so everything else is 0 except for the angle from this pole to this location, which is 180 degrees. So now I've got 0, I've got 1 0 angle. So I got 0 degrees, minus 0 degrees from the pole, minus 0 degrees from the pole, plus 180 degrees or minus 180 degrees from this pole right here. So we know that the real, it's got to be on the real axis in between here. Okay, so we can continue going across, right? So now if we're over in here, well, these two angles, the angles from here and here are still 0, but from this pole to this location is 180 degrees. This pole to this location is 180 degrees. You subtract both of those, you end up with minus 360. So nothing in here is on the real axis. Okay, so how about between here and here? Well, the angles from here to here are still 360, but now the angle from this 0 to this location is 180. So you've got plus 180 minus 360. So we end up with minus 180. So anything in between here is also on the real axis. It's also on the real locus. It's also on the real axis, right? And then finally, if you get out here, well, now we have an additional angle from this pole, and we're back to pointing at 0 or 360 degrees. So nothing out here. So what can we say in terms of real axis? So a couple things. So what's an easy way to do what we just did using the angle criterion? Choose a test point on the real axis. If the total number of real poles and real zeros, so by real poles and real zeros, we mean poles and zeros on the real axis, right? So if they have a complex component, they don't count towards this. So choose a test point on the real axis if the total number of real poles and real zeros to the right of the test point is odd, then the point lies on the root locus. Here's the other way, right? So hopefully most of you have played chess before. And you know how the chess goes black, red, right? So as you go across or any direction. So the root locus forms a checkerboard along the real axis. All right, so let's see if we can make this work. So choose a test point on the real axis. If the total number of real poles and real zeros to the right of the test point is odd, then the point lies on the root locus axis. So let's try this point here. Well, there are 0 poles and zeros to the right of the test point, so it is not on the root locus. If I move over to here, in between here, the number of poles and zeros to the right of this location is 1, right? There's just this one pole. So it's odd, so it's on the root locus. I move over to here. I've got 2 poles to my right, 1, 2. So it's even, it's not on the root locus axis. It's not on the root locus. Move over to here. Now I've got 1, 2, 3. I've got 2 poles and 1 zeros, but an odd number to the right. So it is any place in between here, it's going to be on the real axis. And then finally over here, I've got 1, 2, 3, 4. That's even, so it's not on the real axis. So again, checkerboard pattern, not on the axis, on the axis, not on the axis, on the axis, not on the axis. All right, it's always going to have that same. It's always going to have that same pattern. All right. Okay, so the loci begin at the open loop poles. All right, so I keep writing the same thing here, but so you should, maybe this is important, right? K equals 0 and end at the open loop zeros. And at the open loop zeros, K equals infinity. Now, here's our problem, right? I've got 1 0 here, but I have 3 poles. So where do those other, in fact, I can probably guess that this pole here is going to go to this 0, but where do these 2 poles go? Well, some zeros may be hiding out at infinity. So it's basically a long ways away, right? So so a number of open loop transfer function poles is equal to the number of finite open loop transfer function zeros plus the number of infinite open loop transfer function zeros. So in our example, we have 3 open loop transfer function poles, right? 1, 2, 3. And 1 open loop transfer function 0, 1 finite open loop transfer function 0. So we must have 2 infinite zeros. That's for those other poles. So 2 infinite open loop transfer function zeros. So how do we know we have a 0? Well, we know we have 1 0 at -4. Right? We know we have 1 0 at -4 because if we plug in -4 into here, we get this goes to 0, right? So K G of -4, there really is no H in this case, but if there was, H of -4 is equal to 0. So therefore, -4 is the 0. But also, if we put K, G of infinity, H of infinity, right, because we have more poles, we have more poles than we have zeros, right? So because of that, when we put in infinity, this is also going to go to 0, right? So this is equal to 0, and so that's the key thing, right? Again, more poles than zeros, so therefore infinity is a 0. Well, the question though is, we know if we put in a large number, it's going to go to 0, but the zeros are actually hiding at a particular location. So where are the zeros at infinity? And the loci asymptotically another hard word to spell, right? Approach straight lines at infinity. So if we can find out where these straight lines or these asymptotes are, we're in good business. So basically it's like an arrow pointing where we need to go. So we can calculate the asymptotes real axis intercept. So where does these straight lines, where do they cross the real axis? And that's called sigma 0. And angle theta. Let's call that theta 0 because we use theta for a lot of different things. Okay, so sigma 0 is equal to the sum of the finite poles minus sum of finite zeros divided by the number of infinite zeros, which is what we just calculated. Right? So, and theta naught, the angles that we need, are equal to, this is where we really need this plus or minus. So plus or minus 180 degrees, 2q plus 1 over a number of infinite zeros. Q is equal to 0, 1, 2, how many ever we need. And I'll explain that as we look at our example. So in our example, theta naught, well, let's see. We're going to sum the poles. We're going to subtract the zeros, and we're going to divide by the number of infinite zeros. Well, okay, so let's go back. Where are we here? So we have poles. We can either look at the transfer function here, or we can look at, right, but we have poles at, either way, we have poles at minus 10, 0, and minus 1. So we have minus 10 plus 0 plus 1 minus the sum of the finite zeros. Okay, okay, right, we have a finite zero here at minus 4. You can see it up here as well. Either way. And the number of infinite zeros, right, and that was 2, right, because we had 3 poles and 1 0. So if we plug all that in, we end up with minus 5 divided by 2, or minus 2.5. And then, okay, so theta naught, okay, so theta 0. So let's just go ahead and add that location. All right, so we said it's at minus 2.5, right? So let's do green here. So 1, 2, this location here is sigma 0, which is minus 2.5. And notice it doesn't happen to be actually even on the locus, it's on the real axis, it's not on the root locus. And it may or may not be, that doesn't matter. All right, so we know that these lines, wherever they're going to cross at minus 2.5. So now we just need to find out what the angles are. So theta naught is equal to what? Plus or minus 180 degrees, 2q plus 1, divided by the number of infinite zeros, and I have 2 infinite zeros. So I've got to find two angles, right? Because I've got 2 infinite zeros. So we end up with, well, this is, if I divide by 2 here, I've got plus or minus 90 degrees, 2q plus 1. And so if we plug in q is equal to 0, we end up with plus or minus 90 degrees, right? This is for q equals 0. If we plugged in q equals 1, we'd end up with plus or minus 270 degrees. And we could keep going, but pretty soon we can see right here, we have two angles, right? That's all we need, right? We just need two angles. We can calculate two more angles, but these are actually the same, right? 90 degrees is the same as minus 270, and minus 90 degrees is the same as plus 270. And every angle we get here is still going to continue to point to the same direction. So we really don't, because we only need, right? So for this example, number of infinite zeros is 2. So we can ignore everything that comes over here. All right. So, all right, if we needed 3 angles, then obviously we would need one of these angles from here. All right. It's not going to give you any more angles. It's just going to give you the same angles going forward the further you go to the right. So, okay, so we said that right? So we've got plus 90 and minus 90. So if we go straight forward here, right, that is plus 90 degrees. And actually, let's do, let's do it this way. It won't be as pretty, but we probably want to, because it's not on the, it's not part of the axis itself, right? We have one at plus 90. We're going to use a dotted line here. That's a really poor dotted line. And this angle right here is minus 90 degrees. All right, so those are our two asymptotes. So that's telling us that we have an infinite zero way out here, right? So we're going from here, and it's way out here, and then there's another infinite zero way down here below my screen, right? So what does the locus look like? Well, we can, I guess let's switch to red. So we use red here for, right? So this pole starts here and goes to this 0. These two poles, right? Everything has to, so these two poles, right? Everything has to be reflected about the imaginary, about the real axis. So we know that somewhere in between here, these are going to break off and they're going to go this direction. And this is going to do the opposite over here. So we can refine this later on. But for right now, we know it's going to look something like, let's try this one more time. All right, so this one is, so these, and likewise, this one is coming down here. And those are theoretically perfectly symmetric. So these two, so showing the arrows, that's really important. These two come together. Somewhere they break away. And this one goes towards this 0 out in infinity, right? It's way out there, so I'm not drawing a real 0. And then likewise, this one comes down here, and it is going at some imaginary 0 over here. So you can view these as, these lines here are pointing the direction where those zeros are at. And we're going to asymptotically approach them. So one of the questions that you might ask, right, were we able to stabilize the system, right? Because remember this, we need to be able to fly this, right? Is there any value of K that will stabilize the system? So, I don't like that color. So can we stabilize the closed loop system? Because without any controls, this plane is going to crash. Can we stabilize the closed loop system? And the answer is yes, right? So for K is equal to 0, we have this unstable pool. We have this one at the origin. As K increases, this one comes here, that's always going to be stable. These two are going together, but after some value of K, right, we end up with all the closed loop poles are over here in the left half plane. So at this location beyond, so the answer then is yes. For a large enough K, right? And we could, assuming we've drawn this correctly, we could use the magnitude criterion to actually calculate it. All right, so hopefully this example made sense.